Okay, great. So thank you everyone for being here today for my presentation. So it is called Handoff, Disconnectivity and Energy, where UAV user navigation beyond 5G system. Um, for this work, actually, it's a number of collection of works. So I'll start with a very short introduction about UAVs and their use. Then actually I will talk about 3 different contributions that have been made in my group that are concerned about the connectivity challenges of UAVs when they are used as user in beyond visual line of sight. And also you will see the methods, or let's say the solutions that we have developed in these problems are all machine learning related. So that could be interesting point, maybe some if they're interested to use it. And also finish at the end with the conclusion. So for the introduction, you would all know that UAVs now can be used in different applications, such as aerial video surveillance, traffic surveillance, can be used also in agriculture, precision agriculture, and one of the nice application is really to use it as for cargo delivery, and also it can be used for search and rescue missions and other things. So the use of drones in this type of application, specifically in a beyond visual line of sight application, would really require that we have a reliable link for command and control for the drones. And this has to go through usually cellular, at least for now, through existing cellular networks. So that's why we have what we call now cellular connected UAVs or UAV users as a new type of cellular users that can be flying at high altitudes. And the advantage of that is actually they might have stronger line of sight communication link with the cellular network infrastructure. So these things have been happening the last few years. But of course, with this new type of users, we have a number of questions that we have to answer. So first of all, how to operate these UAV users using existing cellular network infrastructure, how to make sure that communication quality is acceptable. So this is specifically regarding the communication perspective of the operation of the drone. So we've been looking to disconnectivity constraints, for example, on handoff events, etc. And also there is the transportation perspective, where actually when you operate a user or UAV user for a mission, you have to make sure about that it has, for example, enough battery energy to make the mission, about the speed that is using to operate, the trajectory planning, etc. So there is a number of things that we have to solve in order to make the operation of the drones as in a transportation system, as a vehicle in a transportation system, working safely and in the best possible way. So our works, actually, we've been trying to answer some of these questions. And the first one is really easy. So we've been looking into the scenario of cargo UAVs. So cargo UAVs are just drones that are used to deliver items from a warehouse to another place. And this is an example, actually, that I'm showing here. So we have a drone that will just fly, go, drop something in a location, and then go back to the warehouse. So for this type of systems, we really need to ensure that we have reliable communication link with the cellular infrastructure. So with the base station, the ground base station for command and control. And if you see on the right side, actually here on the slide, you'll see this is what it looks like as a heat map from the UAV perspective of ground-based stations. So you can see if it's flying at 20 meters or 40 or 80 or 120 meters, it's not the same heat map. So we have these differences on the strength of the signal, or RSRP, that is seeing. So the darker the color, meaning that we are just going down to a coverage hole. So when it's very dark, meaning that the strength of the signal is so low that actually we are in a coverage hole, or actually in a disconnectivity situation. And based on that, actually, we've been formulating a problem where we want to design energy efficient trajectory here with minimum handoffs and maximum cellular link reliability. So energy efficiency here is really related to the fact that we have energy consumption. So we want to make sure that when we travel over the trajectory, we have to make sure that we don't consume a lot of energy and we respect what we have as a battery level. So this is the battery level. And also we want to achieve minimum handoff. So actually the handoff event is really important because if we have frequent handoffs, this usually would cause a lot of signaling overhead, and this will be negatively impacting even the energy consumption. And here, why I said maximum cellular link reliability, because for now, at least in this first work, we've been looking into the best RSRP that can be seen by a drone, meaning that we will always connect to the best base station that is offering the strongest RSRP. So in our problem, the objective is to minimize energy cost and the handoff cost under constraint of respecting available energy for the battery, and also to respect what we call a disconnectivity threshold. So disconnectivity threshold meaning that the RSRP has to be always higher than the receiver sensitivity to make sure that at least we have a communication link. But if we are below in the sensitivity, we are losing the connection. So we are in the coverage hole or in the disconnectivity situation. And here, the condition that we put here is to make sure that over the trajectory, so that we are flying on, let's say the distance or the sum of the distances that have been traveled where we are in coverage holes with respect to the distance that have been traveled for the whole trajectory is below a given value. So for example, if I am flying for 1 kilometer and I have been in coverage holes for, let's say, 100 meters, so this is equivalent to having disconnectivity of 10%. So 10% of the trajectory I have been disconnected. So we can put here this as a condition also in our system. So this is the problem we formulated, which is actually complex to solve straightforward. And for this one, we have opted for dynamic programming based solutions. So dynamic programming actually is one of the first reinforcement learning algorithms that can be used. And to do this, it's very easy. So we have considered the area where we have our starting and ending flying points for the drone. And we have divided into a grid. So we have these small areas within our area. And we have decided on the action. So since here it's a trajectory optimization, we will just make sure that we are flying each time in the right direction until getting to the destination. And of course, by taking into consideration our constraint about energy, about disconnectivity, etc. So if you look into this one, actually, this is a good example where we have our cargo UAV that have to deliver something from point A to point B, and it is flying at an altitude of 200 meters. And here we consider different conditions for the disconnectivity threshold. So here, as you can see, if the disconnectivity threshold is small, so here, for example, 10%, you see that almost the trajectory is a straight line. And then as we make it more stringent, for example, 0%, meaning that actually we are not tolerating any disconnectivity over the path or over the trajectory, here we can see that actually we are making some more detours because we want always to make sure that we are connected to base stations. So here, actually, these colors are just the coverage areas of some base stations. And then we see how we did it here. So the purple, very dark purple, these are coverage holes. So we really want to go through areas where we don't have coverage holes here. And to give you more insight about this work, so actually here, we've been looking into the energy consumption. So as you can see, if our disconnectivity threshold is really very loose, so here, when it's very loose, you have consumed energy is just linearly increasing with the altitude. I mean, it's just because to get to this altitude, we have to fly up, then to fly in straight line, then fly down. So why it's linear? It's just because when we are adding more distance to fly in the vertical sides from the starting and the ending point, and that's why it is increasing like that. But then if we start having a disconnectivity threshold that is more stringent, so going up to 0%, you see that now it starts to be more complicated. So we're consuming more energy because now at different altitudes, actually, if you remember the heat map I showed you here, so you can see you go up, you have more probability of being in a coverage hole. So here and that's why we have to make more detours, and the more detours you make, the more energy you will consume, and that's why you see this increase in energy consumption. And for this figure, actually, we just evaluated the handoff rate as a function of the altitude. I mean, the first thing is that that we can see is that when we change the altitude, actually there is no pattern between the handoff rate that would happen and this change of altitude. However, what we see is that it is linked to the disconnectivity rate. In fact, that the fact that actually if the handoff rate is increasing inversely to the disconnectivity rate. So here it's the same thing. So meaning that if we want to make more detours to avoid to make sure that we respect the disconnectivity threshold. So actually, if you make more detours, there is a higher probability that you will make more handoff events. So that was for the first work that we did. But then actually in the second one, we have been thinking that now, okay, we did this, we optimized the trajectory, but how about also optimizing the cell association or the association to the base station, and actually giving exactly the same system. What we've been looking at is actually the problem that now at first we were really associating always to the base station that has the highest RSRP. The problem, if you do that, you will trigger more handoff events that are undesirable. So we have changed this and in this system, where actually we will just make sure that RSRP is just high enough to be operating. And also, so now what happens is that when we are in a given 3D location in the air, the cargo UAV can see multiple candidates and has to choose between them. So for sure, if we want to minimize the handoffs, we will make sure that we are connected as much time as possible to the same base station. So here, problem formulation is that we design energy efficient trajectory with minimum handoffs and satisfied cellular link reliability. So here, the difference, if you can see the problem, there are two slight differences compared to the first one. The first difference is that now we have cell association. So now we decide to which base station we have to connect. And the second change is that the disconnectivity condition, we change it from a strict condition or constraint to a component of the objective. So here we want to minimize the distance that where actually we are in disconnectivity with respect to the whole trajectory. And of course, we want to reduce energy consumption and reduce the number of handoff events. So for this problem, now we have proposed a different solution, which is based on Q-learning. So we took the simple one just because we wanted to try and see how this works since the problem is novel. And here actually we have the same thing about trajectory, meaning that we have to move in different directions or along the trajectory, but at the same time we assume that the UAV can sense the RSRP levels that are coming from different base stations around him, and he can make ranking for them. So the one that has the best RSRP, and then the second, the third, etc. And this information is important for the decision later. So since it's reinforcement learning based, we had to define a state for the cargo UAV. So here it is about the location of the cargo UAV and serving cell ID. So the current location and serving cell ID. And the actions is really to move to a different location and decide the association to maybe the same or a different cell ID. For the reward, it is a combination. So it is a little bit of reward design here, where we have weighted function of total traveled distance that reflects energy consumption, cellular link reliability to reflect disconnectivity, and also the handoff rate. So based on that, we have conducted some simulations, and we have developed actually different solutions. So the first one are benchmarks. So we have the shortest path. So this one, meaning this is the straight line between point A and B, without respecting any of the conditions. And the second one is RSRP aware. So meaning that this one is only concerned about the disconnectivity. So we want to make always sure that the RSRP is above the threshold. And then we have our reinforcement learning based algorithms, where actually we have taken the same solution but with different weights. So weights for the energy, for the RSRP, and for the handover. We have taken different values here to see what will be the impact on the solution. So here, as you can see, we have three figures results for battery consumption, disconnectivity, and number of handoffs. And if you can see here for the battery consumption, if we focus only on the flying altitude of 40 meters, here, the red one, so actually you see that all of them almost have the same battery consumption. So meaning that the shortest path is just the straight line, but even for RSRP and the proposed algorithm, actually our trajectory are almost straight line. They are not straight line, they are almost straight line. And you will understand why they are almost straight line. So actually, if you look to the disconnectivity, you see if we were in a straight line, 1% of the trajectory will be in disconnectivity, in coverage holes. But it is 0% for the other ones. So it is 0% for the RSRP because we really want to make sure that we respect, that we avoid disconnectivity. And then it's 0% for the other ones because actually it is based on the same principle in this way. But if you look also to the handoffs events, you see here with the shortest path, we have 30, we triggered 30 times handoffs. For the RSRP, it doesn't care about the handoff. So actually it triggered almost 28. It's about 28 handoff events. But for our solution, we are about, actually here it is about 8, I think. And here it's about 5, 6, yeah, 7, 8 and 7. So the number of handoffs events is really low. And if you see for the different altitude at 80 meters, so now we see we are consuming more energy for these solutions. And of course, that's normal because we are at higher altitude. So there is a lot more areas where there is risk of disconnectivity. So we have to make these detours to go around. So we consume more energy. But when you can see here, disconnectivity, we are also very low compared to the shortest path. And in terms of number of handoffs, same thing. So our proposed solution is really providing the lowest number of handoffs, even though we have changed the altitude. So actually, these two works were really focusing on cargo UAV, mainly on optimizing the trajectory and then seeing also about the association with base station. In this third work, actually, the framework is slightly different. So here we assume that we have multiple UAVs flying in 3D aerial highways, meaning that now we don't move around as we please. We are following, let's say, regulated 3D highways that have been designed over an urban area, for example. So here we take the example where actually we have multiple UAVs that are cargo UAVs flying to deliver some items. And since we have these 3D highways, so actually you can see in this illustration, we have, for example, a highway that have multiple lanes. So the fact that we have multiple lanes, meaning that we can have massive numbers of drones flying in the same highway without really bothering each other. So what is interesting with this new framework is now we have to look into not only a communication perspective for connectivity and disconnectivity or handoff, but also to look into some transportation parameters or metrics. So from transportation perspective, one of the parameters or one of the objectives is really to make fast mission completion. So actually, if I want to be fast, meaning that I have to move the fastest as I can over a lane. But of course, there will be problem of collisions if I just fly very fast compared to the other ones. But here it is as a normal highway, vehicular highway. So we can change lanes, we can move from one lane to another one, change speed and everything. So this is the new perspective that has been added here, where actually we have these two problems. So to be associated to a base station, to have a connectivity with respect to disconnectivity or handoff constraint, and at the same time we have to be we have to make the traffic flow, the transportation traffic flow, very easy and safe. So for our motivation for this work is really that most works previously, they were really focusing only on the communication perspective, and there was really not much interest on the transportation perspective for UAV users on 3D highways. So here the problem is to maximize many metrics. So we have traffic flow for the transportation, and you have achievable data rate, or actually here it's related to RSRP, and to minimize the handoffs. We have here many constraints, so it's slightly different. So of course, we do consider that we have to sense the RSRP coming from different base stations, so to know how to associate to them. But here we added constraint about that, the fact that each base station cannot support more than a fixed number of UAVs simultaneously. And also we wanted to make sure that traffic load is balanced between the base station, meaning that association have to be balanced between the base station. For the optimization parameter, we have transportation and communication parameters. So transportation is mainly about motion in this case, and communication about the association to the base station. And of course, there are all the other metrics that we have to look at regarding this connectivity, handover, etc. So here we have proposed deep reinforcement learning with action branching solution. And I will explain to you later why we had added this action branching. So at first we have our observation space for a drone, so which includes transportation observation, which is kinematics of the UAVs, 3D location and speed, and communication observation regarding the association and RSRP levels that we have to base station. So if I take one agent that is implemented on one drone, so the state that it sees is its own location and speed, the location of neighboring drones and their traveling speeds, and also it will have the same table as previously, so RSRPs of connectivity to a set of base stations that are candidates to which I can connect. And for the action here, we have transportation action, which is lane change or keeping the same lane, or accelerating or decelerating within the same lane. We have communication action is to stay associated with the same base station or to change and associate with a different base station. So we have to define which base station to connect to. And for the reward function design, actually here, it is composed of two reward functions. So we have the transportation reward, and we have been defining it as a weighted function of the traveling speeds outcome. So as we said, from the transportation perspective, for us, the objective is to do the mission faster. So meaning that if I go faster, it's a good thing. But the problem is that if you go faster, there is a risk of collision. And that's why we have added the collision penalty. From the communication perspective, so we have a function of weighted achievable data rate. Actually, it could have been, actually, it's just a function of the RSRP that encourages fairness, and it can be penalized, and here it's penalized by the handoff events or handoff probability. So why this action branching component? So actually the problem is that if we take the problem as it is with all these actions, the action space is really huge and it's very large. If we consider that we have several agents, so here we are not having only one UAV, we have multiple UAVs, and everyone is operating individually, but it has impact on the other ones, and that's why we have this shared observation environment for them. So with the branching, so the solution is to use action branching, is actually to add a decision module that will be shared among multiple network branches. So I'm showing here the architecture where actually you have different branches for your network, deep reinforcement learning network, and each of them corresponds to an action dimension. So for us here, it's easy. We have the communication and the transportation branch, and everyone is taking separate communication or transportation action, and it has an impact on the reward. So on the transportation and communication reward, but these ones with action branching will be combined and will be combined also to recalculate the Q values for the whole system. So the advantage here is really to independently handle each action dimension separately, which result in linear increase in number of network outputs with the degrees of freedom. So with this solution, we have set up our system. So we assume that we have several UAVs that are running over a 3D highway, and we have a number of base station. Actually, we considered most of the case 15 base station that are spread over along these 3D highways to which the UAVs can connect. And actually here we are showing results of transportation reward, communication reward, and also handoff rate that have been achieved. So here we have considered, and I'll just go back here. We have considered branching for deep Q network at first, and then we extended to double deep Q network. So that's what we call BDQN and BDDQN. And you can see here at first we have just evaluated our proposed solutions. We have shown the results for different targeted speed. So targeted speed by the UAVs, it's either 10 meters per second or 20 meters per second. And we have seen different things. So at first, if we compare, for example, green and red, which is I'm sorry, no, green and blue, which are the BDDQN for different speeds. So you see that transportation reward, when the speed is lower, it seems to be doing better. And actually, it's normal because if I'm going slowly, there is less risk that I will collide with the other one. So actually, the impact of the collision penalty will be very small compared to here, where actually I am really traveling very fast, and in this case, I will be penalized a lot more because of collisions. And if you look to the communication reward, actually you can see here, and this is interesting, the blue and the black one. So actually these are BDDQN and BDQN are really close. Okay, so here are really close, and they are slightly different. So actually it's inversed compared to the transportation reward. But the first thing I want to say is that if you look also to the speed, for example, the green and the blue, so the green and the blue, same thing. So actually, if I am slower, I am doing great in communication reward. And this can be explained by the fact that we are doing better because if I have a smaller speed, I will trigger less handoff events. So the fact that we are not penalized for handoffs, or we are less penalized for handoffs, makes our communication reward higher. So as you can see here, we have these actually trade-offs between transportation and communication reward, and also here I'm showing the impact of the handoff. So both solutions are really operating very well, but we have this preference for BDDQN, especially for the communication reward perspective. And here, these are different results. Well, actually, we wanted to see the impact of the number of available base station along the 3D highway, and what impact it would have on the outcome. So the first thing is that we added a benchmark. So here it's called shortest distance-based association, where actually we assume that our UAVs will associate with the closest base station or the closest available base station. So, and here, this SDB is really the gray lines, and we have our solution as the orange and the green lines. So at first, if you just look into the gray lines, you see as the number of base station increases, there is not much variation and the performance. Maybe slightly, we would prefer only 10 base station compared to the other cases. That's the only difference. But if you look into our solutions, transportation reward is really decreasing when we have an increase in when we have more base station available. On the other side, for communication, we see we have some optimal number of base stations. So it's about 15, where actually we have the highest communication reward. And here, if you see the impact on handoff rate, actually you see that if we have a smaller number of base station, it is triggering more handoff events than in the case we have 15. And I will explain you that. So actually what happens here is that when we are increasing the number of base stations, the system will prioritize increasing the communication reward at the expense of the transportation reward. So this is what's happening here. And since here, at first, when we had here 5, for example, we are prioritizing transportation reward, meaning what? Meaning actually we are traveling in a more efficient way, but the problem is that we are associating so badly that we are triggering a lot of handoffs. So this is I mean, the increase here is really compensated in the other way. But what is interesting is that we have an optimal number of base stations that we have to respect for our solution in order to achieve the maximum communication reward here. So to conclude, in this work, we've been investigating the use of UAV user in beyond visual line of sight situations. So we've been looking into the communication perspective, and then we added the transportation perspective, and also we have considered 2 different frameworks where in the first we have some liberty in deciding on the trajectories of the drones, and then the second one where actually we have this 3D highways framework that we have to respect, and where actually the transportation metrics becomes more important. What is interesting also that we have used machine learning based tools, and they are really relevant to solve such problems. And in future work, and this is what we really hope to do in our lab, is really to start making test beds and implementation in real environment. So thank you, everyone. I'm open to your questions.